So in this section, we're not going to simply just look at the graphs of the exponential functions. We're actually going to look at the relationship between the equation and the graph. So the function we have here is y equals e to the power of x. E is a constant. It's kind of like pi. The value of e is 2.7182818289045, and so on and so on. It continues randomly. It continues infinitely. It's a naturally occurring ratio of things that grow continuously, most commonly populations. But we need to make some predictions. The number of x-intercepts. As we saw in section 8.1, all exponential functions have no x-intercept in the manner that we'll study them. The y-intercept of every exponential function will be at a, the coefficient in front of the function. As you can see, we don't have one written, so that means it must be 1. The end behavior. All exponential functions that we will study move from quadrant 2 into quadrant 1. The domain would be all real numbers, just like all exponential functions. And the range would be that y is greater than 0. So we can use the equation. We just did use the equation to make the predictions. To verify if they're correct, create a table of values and graph the function. Well, I've gone to the liberty of graphing it on a calculator. As we can see, we have a single y-intercept. The domain would be all real numbers. It does continue off to the left. It does continue to the right. However, the way the graph looks, it does actually look like it touches the x-axis here. It does not. That's just a limitation of the view that we have. If we were to zoom in on this, we would still see a gap between the function and the x-axis. Even though it would be excessively small because of the asymptote, it would still be a gap. All of our other predictions match up. The domain, the range, the x-intercepts, the y-intercept,